Greetings and salutations and welcome back. In topic 1 we looked at projectile motion, where the acceleration and the resultant force are both constant in direction and magnitude. In topic 2 we're going to look at the motion of a particle travelling in a circular path with a constant speed. This is referred to as uniform circular motion. Even though it is travelling with a constant speed, there is going to be a change in direction. This means that there is going to be a changing velocity. And to produce this changing velocity, we're going to need an acceleration. Now, the direction of this acceleration is always going to be towards the centre of the circle. It is referred to as centripetal acceleration. There are many questions where we are asked to show the relationship between acceleration and the changing velocity. The most common type of question will ask us to use vector subtraction to show that the direction of the acceleration is towards the centre of the circle. To illustrate the difference between the instantaneous velocity and the instantaneous acceleration or centripetal acceleration, I have chosen this question from the 2011 physics exam. The diagram below shows a section of the path of an object moving with uniform circular motion in a clockwise direction. In Part A, it is important to remember that the lines that we draw are both labelled and have a direction attached to them. The first line to draw is the velocity vector. It is a tangent line drawn at point P. Make sure you include the direction on the line and the velocity vector. The second part of the question wants us to draw a line for the instantaneous acceleration. This is going to be a line at 90 degrees to our velocity vector, and make sure you include the direction towards the centre and the appropriate labels. Part B of the question requires us to calculate the magnitude of the instantaneous acceleration. To do this, we are supplied with the speed of our object, which is 5 meters per second, and the radius of the circular path, which is 12 meters. We're going to use this formula to calculate the centripetal acceleration of our object. The first step is to substitute the correct values into our formula and to carry out the operations of squaring the speed of the object. Now you notice that my answer is 2.083. Now given that both of our numbers 5.0 and 12 have only 2 degrees of accuracy, I have rounded off my answer to 2.1. Okay, and I've made sure that I've included the appropriate units at the end, which being acceleration is going to be meters per second per second. Since the object is travelling with a constant speed, we can measure the time it takes to complete one revolution. This is referred to as the period. I have highlighted the relationship between the speed, the circumference, and the time period. The last relationship is between the centripetal acceleration, the speed, and the radius, which I have highlighted here in yellow. The thing to remember is that it is a centripetal acceleration, and so it is always directed towards the centre of rotation. To produce the centripetal acceleration, we're going to need a centripetal force, and like the centripetal acceleration, it is also directed towards the centre of rotation. The centripetal force can be produced by a variety of means. The first example is where our object is connected to the centre of rotation by a physical means, and this is referred to as a tension force. Gravitational forces are discussed in detail when we look at the motion of satellites. Normal forces are discussed in detail when we look at the motion of charged particles in electric and magnetic fields. Frictional forces are used in the explanation of banking of road curves. The weight of the car, which is calculated using mass times gravity, is responsible for the vertical force of the vehicle acting upon the road. Newton's third law requires an equal and opposite force acting on the vehicle. This is referred to as the normal force. And finally, the horizontal force is provided by the contact between the tyres and the road. It is this normal force which provides the centripetal force for the vehicle moving around the banked curve. In fact, it is the horizontal component of the normal force which produces the centripetal force needed. In the following example questions, we will derive the equation tan theta is equal to v squared over rg and the importance of the banking angle, the speed, and the radius of curvature. I have selected this example of a banked curve question from the 2012 exam. The actual diagram is too big to fit on the page, so the first part of the question asks us to draw a vector to show the normal force acting on the bicycle, and then to resolve that normal force vector into its horizontal and vertical components, and to make sure that each component is labelled. I have drawn the normal vector in blue. You will notice that it is at 90 degrees to the road surface. I have then resolved that normal vector into its two components, the vertical component and the horizontal component. They are both in red, and you'll notice that they are at 90 degrees to each other. Also, that all my labels show that they are vector quantities. Part B asks us to state why the vertical component of the normal force has a magnitude of mg. To answer this question, all we simply need to do is to state the fact that the vertical component is in fact going to be the equal and opposite force to the weight of the bike pushing down on the road. In other words, we are using Newton's third law. Part 2 of the question asks us to derive the equation tan theta is equal to v squared over rg. I have included a copy of the diagram we used to answer Part A. Using the tan ratio for the normal force, this will be equal to the horizontal component divided by the vertical component. Now the horizontal component is actually a measurement of the centripetal force, mv squared on r. The vertical component is a measurement of the weight due to gravity, mg. Now if we substitute those two formulae into the ratio, we get that tan theta is equal to mv squared over r times by mg. Now the masses are going to cancel, so what we're left with is that tan theta is equal to v squared over rg. Part C requires us to determine the maximum speed of the cyclist if they're going around a banked angle of 42 degrees, which has a radius of 26 meters. To answer the question, I'm going to use the formula we derived above, which is tan theta is equal to v squared on rg. Now, by rearranging, v squared is equal to rg tan theta. I'm then taking the square root of the right-hand side, and I've inserted the figures for each of the values, so that v is equal to the square root of 26 times by 9.8 times by tan 42. At this stage you might want to check that your calculator is actually measuring degrees and not radians. My answer is 15.15. Now given that the angle is 42 degrees and the radius is 26 meters, I'm rounding off my answer to 15 meters per second.